Hello everyone and welcome to this next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In today's class we will start discussing the concept of support vector machines. Support vector machines are a class of supervised machine learning models which can be used for both classification as well as regression problems. These are based on the concept of hyperplanes that can be defined in feature space, and they use these hyperplanes to either divide your feature space into different classes or to make predictions based on the hyperplanes and the target variable. So, let us go ahead and understand how the support vector machine based algorithms work, because these form an important class of machine learning algorithms, especially in areas such as outlier identification and cases where there is data of very high dimensions. The support vector machine is quite a useful framework. So, let us go ahead and understand it. The topic for today is support vector machines. Or SVMs, right, as they are shortened to. Okay. And support vector machines are a type of supervised machine learning algorithms based on the concept of a hyperplane in feature space. Used to classify data points or make predictions of a continuous target variable. The main idea is that you need to have a hyperplane in feature space. Now, what is a hyperplane? All of us are familiar with life in 3 dimensions, right. We operate in 3 dimensions. There is an x coordinate, a y coordinate and a z coordinate, and then you can define a plane in 3D. In a similar manner, in 2D you have a line, right. If you draw something in 2D, it is a line. In 3D you can draw a plane, and similarly when you go to p dimensions, let us say you have p different features, so you are operating in a p dimensional space. So, there you can define a hyperplane. So, the concept of a hyperplane is central to the machine learning algorithm, that is SVM. Okay. So, that is the characteristic feature of an SVM, and although SVMs were initially developed for classification problems, they have since been adapted to regression problems as well. So, although SVMs were initially developed for classification problems, they were later adapted to regression problems as well. Okay. So, if you look at support vector machines, you can say that they are of 2 types. So, support vector machines SVMs, they can either be for classification, in which they are called support vector classifier, so SVC, or they can be used for regression, in which case they can be called support vector regressor. or SVR. This is true for most of the machine learning models that we have discussed. They always have a regression and a classification counterpart. Even linear regression, there is logistic regression which is used to do classification problems. Similarly, in decision trees you can use them for both classification and regression problems, and the same holds true for a support vector machine as well. Okay. So, there are two types, a support vector classifier and a support vector regressor. Okay. So, let us go ahead and understand how these work and what are the applications in which you would find them to be useful. So, a support vector classifier SVC works by determining the best decision boundary. And like we discussed, for this decision boundary which separates the points belonging to two different classes is a hyperplane in SVM. So, the SVC works by determining the best decision boundary, which is a hyperplane between two classes to achieve binary classification. Okay. And what are the support vectors? So, why is it called a support vector classifier? The support vectors are formed by the points closest to the separating hyperplane. So, that is why the algorithm is called a support vector machine, right, because the algorithm relies very crucially on the decision boundary, the hyperplane which separates two different classes, and the points which are closest to this decision boundary, they are the support vectors and they decide how well the algorithm works, right. So, therefore, the algorithm was named support vector machines. Okay. Now, depending on how strictly the classifier works, I mean you can allow for some errors or you may not allow for any errors. The support vector classifier can either be a hard margin classifier or a soft margin classifier, and this is something we will go into some level of depth. So, like I said, your support vector classifier can either be a hard margin classifier or it can be a soft margin classifier, right, and this is depending on how strictly the separation into two classes is enforced. So, in hard margin classifier you are very strict about it, in soft margin classifier you allow a certain bit of leeway, and that helps you in model training. Training becomes easier, the model becomes more generalizable, right. So, that is the understanding behind this. Okay. So, now that you know some of the basic concepts and meanings of the terms used in support vector machines, let us go ahead and think where we would apply support vector machines in core engineering applications, because at the end of the day we are all motivated by applications. What can we address through the problem of machine learning? Is there really a need for machine learning, or are we just applying it because it is one of the tools that is available to us? It is always important to find out whether machine learning is useful or not before you apply it to a certain problem. So, what are some of the applications that are possible for these kind of algorithms in core engineering? So, let us go ahead and discuss that. So, these are some potential applications of support vector machines in core engineering. And like I always mention, these examples are indicative, right, they may or may not be actually employed, but this is just so as to make you think, and then you can go and try to deploy some of these in your own engineering discipline. So one use case for classification could be fault detection, right, and once you have detected the fault you also want to diagnose what type of fault it is. So fault detection and diagnosis in devices or machinery. So if you are an aerospace engineer or a mechanical engineer, this is something that you may want to use a support vector classifier for, right. Another use case, and this is more close to the discipline of civil engineering, and there you are worried about structures, how stable they are and whether they can withstand various stressors, right, from the environment. So you may want to identify structural damage, for example cracks or corrosion in buildings or bridges. Or even aircrafts. So this is one particular example, right, in which you may use features, right, that you may extract. These could be based on images, they could be based on sensor inputs, they could be based on measuring devices, and then if you put all of them together you can collate them into a support vector machine that can make predictions. So these are a couple of examples. Another example again drawn from civil engineer could be the prediction of concrete quality and strength. And this can be based on, let us say, the composition of the mix as well as curing conditions. How do you let the concrete cure? So these are the kinds of models that you can develop, and again the quality could be more of a classification problem, the strength, the compressive strength of the material could be more of a regression problem. So you can think of both SVCs and SVRs. Another example, this time derived from electrical engineering or power engineering, could be for example load forecasting, right, to predict electricity demand in a locality, and this could be based on various factors, the time of the year, the temperature of the day, the kind of season we are in, the time of the day, whether it is day or night, right, so many other factors, and the population, and whether it is a vacation or it is a weekday, and so on and so forth. And this could be very important, particularly because we are talking about energy storage, right. We want to know how much of the renewables we can use, like solar, wind, how much of it has to be stored in batteries. So all of this load forecasting can play a very important role in the near future, right. Some more examples are for instance quality control of the composition and morphology during drug manufacturing. So you are making a drug molecule, a medicine, then you need to be sure that the composition is right, the quality is controlled in terms of the morphology, the tablets that are being made will they dissolve properly, will they be stable during packaging, and so on and so forth. That has to be determined. And some more examples could include from materials engineering, the classification of materials microstructure. And then predicting what kind of properties the material has. What is the strength of the material? Does the material is it conductive or is it resistive? Is it a semiconductor or an insulator? Does it have a band gap? These are the kinds of questions that you could predict through both classification as well as the regression problems. And finally, in the discipline of environmental engineering, you could develop a classifier to predict the air or water quality. Or you could be more quantitative and tell what is the amount of pollutant or impurity that exists in the air or in the water. So these are just some of the use cases of support vector machines, and I wanted to take some time to remind you about this because it is important to keep the applications in mind as practitioners of core engineering disciplines. Okay, so now that all of this has been discussed, we can go ahead and start to understand how these support vector machines or support vector classifiers really work. Okay, so let us take an example, and this is just to give you some intuition, and we will go more into the depth later. I am going to consider a simple example where there are only two features. Okay, so we are operating in a two dimensional feature space, and as many of the contrived problems that we have been looking at, this obviously may not be true in a real world scenario. You will have many more features where it seeks to illustrate what is happening just if you look at two dimensions, right. So what is happening here is that there are two classes of data points, right. This is one particular class I am drawing with squares, and then there is another class that I am drawing with circles. Okay. So what we do in support vector classification is we find a hyperplane, right, and that I am drawing here in the dashed red line. So this is the decision boundary, and then these are supported by the so called support vectors, right. So you have a support vector here, and then you have another support vector here. So you can see that these support vectors are passing through the points that are closest to the decision boundary. Okay. So whatever is drawn in blue here, these are the support vectors, and then based on which side of the hyperplane, right, here is just a line because we are in two dimensions, which side of the line the points are lying, you can classify it to be of one type. So the predicted variable would be +1, right, class 2, and then here it will be class 1, okay, yi equal to -1. So this is the way in which a support vector classifier works. Okay. Now you must be asking, right, is the support vector machine model restricted to a linear decision boundary, right, because the way I have drawn it, right, or even a hyperplane typically is a linear construct, right, it depends linearly on the feature. So can you not use it for non-linear decision boundaries? And it is a very valid question, and the answer to this question is yes, right. So although I have drawn a linear separating hyperplane here, as we will see later, note that SVCs, support vector classifiers, can also be used for developing non-linear decision boundaries, and this is achieved by the use of appropriate kernel functions. Non-linear kernel functions. Okay, a kernel function is just something that transforms your linear space to a non-linear space, and they are used to make the decision boundary a nonlinear one, because in many problems the points may not be separated by a linear hyperplane, but they may rather be separated by a nonlinear decision boundary. Okay. So, this is how a support vector classifier works, it is quite intuitive. Now, you may ask, how does a support vector regressor work, how does an SVR model work. So, let us spend a few minutes understanding that. So, on the other hand, a support vector regressor SVR works by fitting again a hyperplane to predict the target variable right, which is continuous such that most points lie within a margin of tolerance, right. So, the model as we discussed with the hard margin and the soft margin classifier, the support vector machine model understands that there can be errors made in prediction. So, what you try to ensure is that most points lie within a margin of tolerance, but you do allow for that margin because you are using a hyperplane to predict the target variable. Okay. Now, one thing to remember is that kernel functions can also be used within SVR, right. So, to introduce non-linearity. So, kernel functions can also be used within SVR to introduce non-linearity. Okay. So, how does this now work? Let us go ahead and try to understand the mathematics behind it. Okay. And we will start with linear support vector classification, and that too a hard margin one. So, the next topic that we are going to consider is linear hard margin support vector classification. Okay. So, I hope you understand what is meant by these terms. It is linear because we are not using a nonlinear kernel function. You already know what is meant by support vector classification, and we also briefly discussed what hard margin means, that you are very strictly enforcing the separation between the two classes. Okay. So, let us see how this kind of a model would work. So, the input to the model is basically a feature vector, right. So, xi means the ith data point, and usually we have been using a model with p features, right. So, p is the number of features and xi is just referring to the ith data point, and the notation used here means that these points, right, all the features take only real values. Okay. So, that is something we are assuming in our formulation. Okay. So, this is what is happening, and what is the prediction that we want to make? The prediction desired is essentially the label yi that can either be -1 or +1. So, if it is -1, that means the point is of class 1, and then if it is +1, that means the point is from class 2, the second class. Okay. So, what is the goal here? As you already know, the goal is to find a hyperplane okay, and that hyperplane equation will be beta transpose x plus beta naught equal to 0. Okay. So, that is the hyperplane we are looking at, and as used in the notation with linear regression, this is basically a constant, but this beta transpose it is a vector of weights, right. So, the constant is also called a bias, and then this is a vector of weights. So, there are p features, so there have to be p weights. So, then when you multiply them, basically you are taking a dot product between the weights and the features. So, I am writing that as beta transpose x, assuming that x's are row vectors and then beta is also a row vector. Then if you take beta transpose, that will become a column vector, and then you will get a scalar here basically. Okay. So, this is the hyperplane that we are after, and the desire is that this hyperplane can separate the data so that one set of points, right, is falling in one class and the other set of points is falling in the other class. So, essentially we write it in this way. So, yi times beta transpose xi plus beta naught is greater than equal to 1 for all I. Okay. So, this equation is at the hyperplane. Remember that when you are talking about a point xi, right, here, that may not or ideally will not lie on the dividing hyperplane, it will lie on either side of the hyperplane, and that is why beta transpose xi plus beta naught, that is not 0, right. This is 0 exactly on the hyperplane. What we are now talking about is data points that will most likely not lie on the hyperplane. So, then we can write this particular condition here. Okay. So, now like we discussed, there are two possible labels, plus and minus 1. So, let us see what happens when the label is plus 1 and what happens when the label is minus 1. So, therefore, when yi is plus 1, what this means is that beta transpose xi plus beta naught will be greater than equal to 1. So, that is the condition, and when yi equals minus 1, the condition is that minus of beta transpose xi plus beta naught is greater than equal to 1. So, you can multiply throughout by minus 1, but the thing is when you multiply by a negative number, the sign of the inequality flips, right. So, this becomes beta transpose xi plus beta naught less than equal to minus 1, right. So, these are the two conditions, right, that are going to be satisfied. Okay. And we can go back and again draw the diagram that we had shown a little while back, where it had become clear what the hyperplane is, right. And although we had sketched it in 2D, it is really applicable for any number of dimensions, right. It is just we are sketching a 2-dimensional version of it. Okay. So, this is x1, this is x2. So, you had two classes here, this was one particular class, and then you had another class here, and you had the task was to find this decision boundary or the hyperplane, and then there were two sets of support vectors, right, which were drawn. Okay. Now, we will now define what is meant by margin, right. So, the word margin has a very specific meaning here. This is the class yi equals plus 1, this is the class yi equals minus 1. So, if you look at the distance between the perpendicular distance between the decision boundary and the support vector, this distance is called the margin. So, that is the closest distance between the support vectors and the decision hyperplane, right. So, this is the support vector and this is the decision hyperplane. Okay. So, the whole idea in support vector machine is you need to find out, right. So, we need to find beta and beta naught, right, such that the margin which we have defined here as the distance between the support vector and the decision hyperplane is maximized, right. So, we need to find the hyperplane beta and beta naught, specify the hyperplane such that the margin which is the distance between the hyperplane and the support vector is maximized. Okay. So, how that is done mathematically, we will discuss that in the next class. So, to briefly recap, in today's lecture what we did was we introduced the concept of a support vector machine. A support vector machine is a supervised machine learning algorithm which can either be used for classification or for regression problems, and the support vector machine is based on the concept of a hyperplane, which is just the extension of the concept of a plane in 3D to a plane in the feature space, and then using this hyperplane you can either separate the data into various classes, so that is a classification problem, or you can use the hyperplane to make predictions of target variable, which makes it a regression problem. So, I hope you like the content today. Thank you for joining and I look forward to seeing you next time.